Color is the visual perception created when light interacts with a surface and reflects specific wavelengths to our eyes, meaning the color we see depends on how a coating absorbs and reflects light. The foundation of color theory starts with primary colors, red, blue, and yellow, which cannot be created by mixing other colors. Mixing two primary colors produces secondary colors, such as orange, green, and violet, while tertiary colors are formed by mixing a primary color with a neighboring secondary color, resulting in subtle shades like red-orange, yellow-green, or blue-violet that are critical for fine hue tuning. In color science, hue defines the basic color identity. Chroma represents saturation or strength, and lightness describes how light or dark a color appears, corresponding to visible wavelengths from roughly 380 to 700 nanometers. In automotive coatings, color precision is critical because even small deviations directly impact perceived quality and brand identity. Color is measured using spectrophotometers under defined illumination conditions, typically D65 daylight. Solid colors are often evaluated using single-angle measurement at 45 degrees per 0 degrees, while metallic and effect coatings require angular measurement because aluminum flakes, mica, and interference pigments reflect light directionally. This directional behavior is described through face, flop, and travel, where face is the head-on appearance, flop is the low-angle appearance, and travel is the visual transition between them. In production environments, three-angle spectrophotometers are widely used, typically measuring at around 15 degrees, 45 degrees, and 110 degrees, where 15 degrees captures face brightness, 45 degrees represents the mid-angle appearance, and 110 degrees captures flop behavior. While multi-angle spectrophotometers used in development and master approval measure 5 or more angles to create a complete optical fingerprint of the coating. Beyond formulation, process parameters strongly influence color appearance, starting with viscosity. When viscosity is too low due to excess thinner or high temperature, the coating film becomes thinner and more fluid, allowing metallic flakes to settle and align more parallel to the surface, which increases face brightness, lightens the color, and can reduce flop contrast, sometimes causing a washed-out or silvery look. When viscosity is too high, flake mobility is restricted, leading to poor orientation, increased light scattering, darker appearance, reduced sparkle, and sometimes a muddy or grayish flop. Dry film thickness plays a similarly critical role. Higher DFT increases light absorption within the film, making colors appear darker, deeper, and more saturated, while lower DFT allows more substrate influence and light reflection, making colors appear lighter and more metallic. In effect coatings, even a 2 to 3 micron DFT difference can significantly alter face-to-flop balance. Temperature and humidity further complicate color stability. High booth temperature accelerates solvent evaporation, reducing flake reorientation time and freezing metallic orientation early, often leading to higher face brightness but unstable flop, while low temperatures slow evaporation, increasing sag risk and causing non-uniform flake distribution. High humidity can lead to moisture condensation, solvent imbalance, and delayed evaporation, increasing the risk of mottling, patchy metallic orientation, and color cloudiness, while very low humidity accelerates solvent flash-off, again limiting flake alignment and increasing shade variation. Airflow also interacts with these factors by influencing evaporation rate and pigment movement across the panel. Because of these sensitivities, color approval in automotive laboratories must include both instrumental measurement and controlled visual evaluation under multiple light sources, such as D65 daylight, TL84 or F11 fluorescent, A-type incandescent, and LED lighting, to detect metamerism where colors match under one light but fail under another. Substrate differences between metal and plastic parts, clear coat effects on gloss, DOI, and light scattering, and curing conditions in the oven further modify final appearance. By controlling viscosity, DFT, temperature, humidity, spray parameters, and measurement geometry, and by using single-angle, three-angle, and multi-angle spectrophotometers correctly, automotive coating teams can achieve stable face, flop, and travel across all panels and plants. If you've seen color shift due to viscosity, DFT, or booth conditions on the line, share your experience in the comments and tell me which parameter causes you the most trouble.